you can find us online at rce-cast.com. You can find the entire back catalog there, all of these episodes we've been doing for these good number of years here. I also have again here Jeff Squyres from Cisco Systems and one of the authors of OpenMPI.
Hey Brock, how's it going?
All right. As for upcoming events, I will be in mid to the end of March at University of Illinois at the Advanced Research Computing on Campuses, which is part of the ACI-REF series of projects out there. I will be there, so if you're going to be there, please drop by and say hello. Also, there's going to be a number of deadlines coming up for the Exceed 16 conference. That's the XSEDE, Extreme Scientific Engineering and Discovery Environment. This is the successor to TeraGrid. There's a whole number of items there coming up, tutorials, papers, other things coming up there. So please take a look at those if you're interested.
Okay, so Brock, we got something a little different today. This is different than the normal straight old HPC software or vendor kind of thing that we normally do. But this is something actually people may have heard about in the news before because they have made the headlines a couple times. We are going to talk to the people from D-Wave, the quantum computing people. So, Brock, I wonder if you could tell us who our guest is.
Yeah, so our guest today is Denny Dahl, who is from D-Wave. Denny, take a moment to introduce yourself.
Yeah, hey Brock. I've been with D-Wave for a little more than 4 years. I'm a physicist, and right now I'm actually at Los Alamos National Laboratory. I'm on assignment here. Los Alamos purchased a system from our company about a few months ago, and I'm here helping the users get up to speed.
So can you tell us a little bit about D-Wave, maybe a little bit of history?
Oh, yeah, sure. So D-Wave has actually been around for a lot longer than most people think. The company was founded in around year 2000. We've been using venture capital since then. We were founded by Geordie Rose, who is a physicist from the University of British Columbia up in Vancouver in Canada.
Now, what can you tell us? Start at the high level here. What exactly is quantum computing? Because I think there's a lot of information out there, but from a semi-technical audience perspective, how would you describe what is quantum computing?
Sure. Regular computing, or as we actually call it now, classical computing starts from this notion of you've got a bit. You can control a bit. A bit can be a 0 or a 1. But over the last 100 years, physicists have realized that if you kind of tunnel deeply enough through the layers of nature, at its heart, nature has this quantum mechanical aspect to it, which means systems are not just a 0 or a 1. They actually exist in these superposition states. And so the whole notion behind quantum computing is to start from that point of view and use the fundamental superposition aspect of really the basic building blocks of nature to build a different kind of computer than we normally think of having.
And when you say different, what do you mean by that? Because it sounds like that is fundamentally different and is going to affect everything from soup to nuts in the design.
Absolutely. That's certainly true because with a classical computer, you can imagine that you've got, a number in a register and another number in another register, and you can ask the machine to add them together, and you're going to get a deterministic result. The same thing will happen every time. But with a quantum computer, at its very core, you don't just put a single piece of information into a, quote, register. A register in a quantum computer holds a whole superposition of different information states at the same time. And so when you operate on, a collection of information like that, your results are necessarily probabilistic. So it means you have to think through your computing model starting all the way at the ground up.
So why would we even want to do this? I mean, normally we like to just do regular old math. So what's supposedly so great about quantum computing?
Sure, it's a great question. One of the guys in the physics community who made this suggestion, that we should look at quantum computing decades ago was a fellow by the name of Richard Feynman, and Feynman observed that certain kinds of physics problems that you might want to simulate on a computer can be simulated efficiently. things like partial differential equations and whatnot, you can map them onto a classical computer and get reasonable efficiency. But there are certain kinds of systems in nature, Feynman observed, there are certain kinds of systems in nature that do not have this character. These so-called quantum physics systems cannot really necessarily be efficiently simulated on classical computers. And so Feynman made the suggestion, I think back in the 80s actually, that in order to do a good, efficient job of simulating some of these quantum physics systems in nature, we're going to have to build a new kind of computer, a quantum computer, as opposed to a classical one.
So quantum computing, and when you read it in the news, is talked kind of like as this holy grail, and it's going to solve all these problems. But you're actually building machines today. So what people think about as a perfect quantum computer, is that what you've actually got, and you've got a complete revolution, or are you like on the path there and you've got something that's quantum-like?
Oh, actually, good question. My personal opinion is where we are is on the path. We don't have today a perfect quantum computer, and I'm not actually personally convinced that such a thing as a perfect quantum computer will ever be buildable. But the idea that we have right now is we know how to put certain kinds of quantum mechanical devices together to make a useful quantum computing engine. It may not be the most general possible one that people may wish to that they can envision, but what we have is kind of a starting point which we think will allow people to get their feet wet and actually start to experience what quantum computing is like and how it differs from classical computing.
All right, let's talk about one of those things. So the typical model of classical computing that is discussed is a Turing machine, right? It has a start and an end and a bunch of sequences that goes between the two, to put it super crassly, right? Is that the same here, or are we looking at just a fundamentally different model?
Well, that's a great starting point. In fact, after Richard Feynman, made this suggestion that classical computers were not really going to be great at simulating certain kinds of quantum physics systems, it took another person to sort of take the idea to the next level, and that was David Deutsch. And I think it was in the late 80s that Deutsch did kind of the reasonable thing, based on the idea that you have, or that Alan Turing had, decades ago. Deutsch said, let's take a Turing machine, which, it does exactly as you said. It starts off in a state, it reads something from a tape, it looks up some information in a table, it writes down a new symbol on the tape, and then it moves to a new square on the tape. So that's your classical Turing machine. Deutsch took that concept and he said, let's replace each of the steps in that process with quantum mechanical steps. And what that means literally then is that, when this quantum Turing machine enters a new state, it's not actually a new state, but it's a superposition of states. So that was actually kind of the first or the next step forward in the whole quantum computing, thought process. The idea was, how do we take something as simple as a Turing machine and recast it in the framework of, quantum mechanics?
So how do you exactly represent these quasi-states where there's a superposition of two states? And also, a lot of times in quantum mechanics, you have a probability of being in one state or the other. So you are more towards one or the other, but you don't necessarily know. How do you do all of this? How do you represent it?
Sure. Well, the representation, it's in some sense starts off being very simple. Instead of a qubit being a 0 or a 1, the words we say is a qubit can be in a superposition of the 0 and the 1 state. And literally what that means mathematically is, instead of just saying, my qubit is 0 or my qubit is 1, now I have a weight. And it turns out to be a complex number, but I associate a complex number with the 0 state and another complex number with the 1 state. And the magnitude of those two complex numbers tells me, in effect, does my system lean towards being a 0, or does it lean towards being a 1, or maybe it's in a 50-50 superposition of those two states. So that's the starting point. That's how one qubit is described mathematically.